Okay, this is lab 2-5, combination circuits. The purpose of this lab is to, most loads are connected in series with some sort of control device. The control device and the load are then connected in parallel with another load and control device, which is also connected in series. This type of circuit is neither a series circuit nor a parallel circuit, but is known as a combination circuit. When analyzing these combination circuits, some parts of the circuit require the application of series rules, while others require the application of parallel rules. As an electrician, you will constantly encounter this type of circuit. All right, so what we did in the Learning Hub in the virtual classroom is we broke down the analyzing combination circuits using a numbering system. You'll see that the diagram in this lab is exactly like that worksheet. So in a previous video that I've also uploaded on the Learning Hub, you will see that I broke down the numbering system of that and then the redraw of how that circuit would appear. Okay, so what I've then gone ahead and done is I've built this lab up. The hardest part that students typically have when doing this lab is following all of the, you can see there's a fair amount of connections going on up top here, and understanding where the different jumpers are. Here I've labeled, it looks like, oh no, there we go. We got A, B, C, and D. Those are the jumpers that appear in your drawing. Okay, they're going to ask us to take current values and voltage measurements. I've connected up this fluke meter as my ammeter for the entire circuit that is asked for, and then I have a fluke multimeter here that I'm going to use to measure my voltage drops, and then when they ask us to use a clamp on, an AC clamp on, I've got that here so I can measure the actual current values at each of the loads or wherever they ask us to do so. Okay, so without further ado, let's start with step one. So they ask us to ensure the main breaker's off, which we've done. Okay, study the wiring and then connect everything up. So we've got loads 1, 2, and 3. These are the 150 watt light bulbs. Okay, they are parallel connected if you remember the diagram that we just redrew. Okay, but they are series connected with the cone heater number 4. Loads 7, 8, and 9 are also parallel connected with each other. However, they are series connected with cone heater 5 and cone heater 6. So you're going to see when I power this up that the 150 watt light bulbs here will be quite bright in comparison to these ones, because these are only sharing their line voltage with one cone heater, whereas this side of the circuit has 2 cone heaters, which are taking a fair amount of the voltage drop away from what's going on over here. All right, so let's fire this guy up, see what we get. Turn some power on. They say to energize the circuit. Okay, nothing working until we get that fired up, and you'll see these are burning fairly dim, but those are a little bit brighter. Still not full brightness though because of that cone heater. And what it shows is they ask us for step 5, record the ammeter reading. So we've got roughly 4 amps, okay, or 4.1, but I'm going to call it 4. Our voltage output is about 111 volts. We can just determine that. We're not at a 120. Okay, so our source voltage is 111, and we're going to call it 4 amps is what our output current is. Just keep a nice round number there. Okay, so then they're going to ask us to measure and record the following voltage drops. We got loads 1 through 9 basically. All right, so I've already given you the source, which was 111. Then they ask us to do loads 1 through 9. So 1, 2, and 3 should be the same. And they are sitting at about 63 volts on each of them, and they're exactly the same, which we expected. Okay, and if we subtracted 63 from 111, we're going to see the remainder going across load number 4, because it's in series with it, which is 47 or 48 almost. So that's 111 in total. Okay, so 48 for load number 4. 63 for each of the other ones. Okay, and then we're going to go through cone heater 5. Cone heater 5 is sitting at 38. Cone heater 6 is sitting at, going to be about the same, 37.5 to 38. Okay, so that's 76. So the remainder taken away from 111 will be what's left over here, which isn't a heck of a lot. We've got about 35, 36 volts there across load 9, load 8, and load 7 are all exactly the same at 36 volts, okay? So loads 5 plus loads 6 and then the parallel 7, 8, and 9 should equal 111, which they do. All right? Then it says, next step, using the clamp-on, take the following current measurements. So they want to know what the current value is at the different jumpers. All right? So I've got my ammeter selected on AC amps, and they want to know the current at jumper A. So jumper A, if I reflect back to the board there, it shows jumper A should be capturing all of the current in the upper line. Okay, and it should be the same as D. So here we've got roughly 2.3 amps, okay? And D should also be 2.3 amps. It's coming up there. 2.2 something, 2.3. So basically we'll call those the same. And then C and B should be the same because they are capturing the current on the other branch of this circuit, all right? So C and B is 1.7 at C and 1.7 at B. Okay? So if you added the 2.3 plus the 1.7, that comes to the line current of roughly 4 amps. Now the difficulty or the problem with a clamp-on meter like this, as we've talked about in class, is it does some rounding because it only goes to 1 decimal place. So it's not as accurate as maybe this guy would be. But either way, it's ballparking it really, really close. Okay? So the next question that they're going to ask us to do, in our observation conclusions, they ask us to do a couple things in here. So I'm going to just power this down real quick, and I'm going to skip ahead to question number 6. Which other loads would stop dissipating power if an open occurred at load 5? Okay, so load 5 is that cone heater there. So I'm just going to basically disconnect this jumper here. And in doing so, I'm creating an open in that circuit. Okay, if I power it up, load number 5 was connected in series with the parallel portions of our light bulbs, 7, 8, and 9. And then also that's in series with cone heater number 6. So by removing cone heater 5 out of the equation, we're going to stop all current flow through that lower branch. So you're going to see this side is unaffected, but this side will be affected. In other words, we have no current flow. Okay, so we power back up and it's exactly like I just said. Loads 1, 2, and 3 and cone heater 4 are operating fine. However, 5, 6, 7, 8, and 9 are not working. And if I were to take my meter and meter from that jumper over to here where it was, you'll see that I would see the open 111 volts that we anticipated. Okay? Power that down. I'm going to replace this jumper to there. Okay? And then the next thing, question 7, they said, which other loads would stop dissipating power if an open occurred at load number 2? All right, so I'm going to use my quick hands here. I've just unscrewed this light bulb. It's a little warm. Okay, I've created an open there now. So what you'll see is by creating an open in those parallel connected up light bulbs, you're going to see less total resistance there, okay? Meaning now we should actually get a little bit of a greater voltage drop across there, which would in turn allow for a little bit brighter of light bulbs. It doesn't, in other words, the current doesn't have to disperse as much as it once did, okay? So we'll power that up. You'll see these are slightly brighter, okay? And if we step back and recall, our voltages across those light bulbs or the loads were 63 volts originally. If I meter that again, you're going to see that they're probably fairly close to being the same. Oh, they're actually about 77 volts now. So they've gone up about 15 volts, okay? And that's because the total resistance changed in that component there, okay? This side of things was unaffected. Cone heater 4 is still dissipating some heat too, okay? But just load number 2 was taken out of the equation, thereby altering the results of the loads 1, 3, and 4. Okay? Total current went down a little bit to 3.4. All right, so we'll screw that light bulb back in. And then the next thing they ask us in question 7 or question 8, they said if a short circuit occurred across load number 8. So load number 8 is this light bulb here, and all I'm going to do is I'm just going to put that jumper in, and I'm now bypassing the current flow through that. So in doing so, all of these light bulbs are also in parallel with that, so they've all now been shorted out too. So you're going to see no brightness of lights in here, but cone heater 5 and cone heater 6 would see roughly about 55 volts apiece. In other words, they are going to share that voltage of the 111. Okay, so nothing going on here, but if I measured the voltage drop across cone heater 5, you're going to see it's about 55 volts, and cone heater 6 should be about the same as well, 55 volts. Okay, that adds up to very near the 111. Okay. But the other side of the circuits, nothing changed there, everything is still operating, okay? And then the next thing they ask us to do, if a short circuit occurred across load 7, what effect would it have on the power dissipated by load number 4? Well, we just short circuited load 8, and we saw the results there. If we go over here and short circuit load 7, you're going to see that remember, it doesn't affect anything on the other branch, okay? That's still operating, so it has no effect at all. All right, so I'll power that back off. And then the last question they said is if jumper B was removed. So we're going to take that short circuit out, and we're going to remove jumper B. And in doing so, what we've done is we've created an open on that lower branch of the circuit. Okay, so we won't get any current flow between from cone heater 5 through lights 6, 7, and 8, or sorry, through loads 7, 8, and 9, and then cone heater 6 as well. Okay, so power him up, and you can see, once again, we have nothing. Okay, so that's that. We'll power down. I'll clean up my station. All right, and that is lab 2-5, combination circuits.